Yeah, recording. Okay, so last week we ended here on whether we went past here already, which was on the external merge sorting. And so we had kind of an algorithm how we can do the merge sort. I think maybe let's go through the algorithm first. The algorithm looks like this. At first, let's assume that the memory is able to hold n blocks. The first thing we do is we want to divide it into a number of sorted runs. Okay, so divided into a number of sorted runs, and that is in the divide stage. In the merge stage, we will have a size of the input buffer versus the size of the output buffer. And input will be n-1 block, and output will be 1 block. And the number of runs, they decrease by a factor of n-1 in each merge pass. Okay, let's look at this. I think I have this formula of, where's my formula of, I don't have it. So anyway, let's look at this first. So in this scenario, m is equals to 3, which is the number of blocks the memory is able to hold. One tuple is 1 block. So the size of one run is equals to 3 tuples. And in this scenario, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 12 tuples in total. And so the number of runs equals to 12 divided by 3, which is 4. So this is my first run, second run, third run, and my fourth run. So there are 4 runs in this when the runs are being created, and so this is how this looks like. Then we do the merge pass. In the merge pass, we have n-1 as the input and 1 block as the output. We'll go through how this works later on, but essentially you can just consider it to be like 2 pointers as the input and the output as 1 pointer. Yeah, so you'll just move along the way as and when, just like your typical merge sort algorithm. Okay, similarly for this as well, and similarly for this. So these are all your merge passes, and yeah, so this is the divide, and this is the conquer. So this is how the divide conquer algorithm works. Okay, so this is what I went through earlier. We went through a few examples. So in this example, we have 3 blocks in memory, 2 tuples, 1 block. So this means that in my memory can hold 6 tuples. So from 1 to 6, 11 to 12, 13 to 18, 19 to 24. So in the in the run creation, we create 4 runs as here, and this is the divide step. And in the conquer, 1 to 12, and then typically this is in the conquer step. Okay, I went through this last Thursday, so I probably won't go through this in that much of the detail. Let's look at this next example. I have 48 tuples. Each block holds 3 tuples. M is equals to 4. And so the memory can hold 12 tuples in total, 4 times 3. And so this will be 4 runs. Run 1, run 2, run 3, run 4. Okay. So in this scenario, this will be from 1 to 12, 13 to 24, 25 to 36, 37 to 48. Okay. Okay. In this particular scenario, in fact, in the merge step, what is actually possible is because m is equals to 4 over here. Okay, so if we go back to the algorithm, we load the smallest tuples from the m minus 1 runs into the input buffer. So what can occur here is that I can load run 1, 2, and 3 into the input buffer. To have 1 all the way to 36. So this is a possible scenario. And then thereafter, in my second merge step, carry this out. So this is a possible scenario for this example. I'm trying to decide if am I talking to myself or not. Okay, anyway, go on. Okay, so the cost. So let's say let's say we have BR, which is the cost of which is the number of blocks in R. So in the first stage where we create the run, we incur a cost of 2 times BR. So in the reading and the writing, yeah, so we would first incur this cost as we are creating our run. So this is the divide stage. So this is the cost that is being incurred. The number of runs will be the ceiling of the number of blocks divided by m. So this is the ceiling, the formula to calculate the number of runs in our initial divide stage. The number of merge passes will be the number of runs log of m minus 1. How we can think about this is that for a binary tree, height of this is log 2n. For a called a ternary tree, height of this is log 3n. So for m minus 1 merge passes, the height of this is going to be m minus 1. And the number of so-called nodes is equals to the number of so-called individual runs, which is equals to BR divided by M. Let's see if this makes sense or not. Yeah, I think we can. I think we can make this so-called an assumption. Yeah, I think we can make this assumption that the number of passes, this will be BR over M, and the log M minus 1 will give me the height of my tree. And so at every pass, we read and write every single block. Okay, so this is the height of the tree. This is the height of the tree. And at every conquer stage, we incur this multiplied by this. So 2BR multiplied by log M minus 1 BR over M. And we also incur this at the initial divide stage. And so the cost will be equals to the sum of these two values. Okay. Okay, I hope this is clear. No, it's open book. Open book, so don't never need to memorize anything. Yeah. So you want, you just copy down all this formula in the in some place. Some place. Yeah. But it's better to understand. Better to just understand how this comes about. So if we think about it, this is the if we compare this to a tree, this is something like the number of leaves in the tree. Because this is like the like that. So this is something like the number of leaves in the tree. You can think about it in this manner. Okay, so it will be a bit more intuitive. Okay, we have now have one put it question. So maybe you all try this for the next maybe 3 minutes. Try to do this. Yeah, so we'll be sorting based on the second attribute. No lah. Yeah, I think we are sorting based on the second attribute. Yeah. Okay, let's try. Maybe you take about 2 minutes to try this. Let's see if I have the solution somewhere. No, I don't have the solution here. Yeah, so we have to do it ourselves. Yeah. So yeah. So yeah. So let's maybe I take the next 2 minutes to do this. Thank you. So it's 1, 2, 3, 4, 5, 6. So there are 12 records in total. Okay, let's start. So there are 12 records here. And what will happen is that memory holds at most 3 blocks. And so first thing we do is calculate runs. So number of runs will be equals to 4. So where's my mouse? Okay, so 1, 2, 3, 4. In each run, we will have 3 records. For simplicity, I'm just going to write down the numbers. So I have 17, 21, and 1, 13, 3, and 8, 4, 11, and 6, 9, 2, and 12. Okay, then after that, because it's 3 blocks, so I'm going to do m minus 1. So in this scenario, I will be combining these two and then these two. So this is what is going to happen. Oh, sorry, when I do my sort, merge, divide, I forgot to sort them first. So I need to sort them. 1, 17, 21, 3, 8, 13, 4, 6, 11, 2, 9, 12. Okay, so in my divide stage, so now I'm going to my conquer stage. So be 1, 3, 8, 3, 8, 13, 17, 1, 2, 4, 6, 9, 11, 12. Okay. So then of that, yeah. So this is just a typical merge algorithm in your merge sort. So I don't need to go through so much. Okay. So as long as you get the first one correct, and then you can find out like what is the next step m minus 1 to merge from, then you're actually pretty on track already. Can? Okay. Any questions before I move on? If there are none, we will go on to our next lecture. So, we will be using this as the running example. Okay, this part is maybe a little bit a lot of theory. So yeah, so need me to repeat, let me know. Okay, so this is the running example. There are 2 tables, student and ticks. So the number of students is 5,000. Number of blocks in student is 100. Number of ticks is 10,000. Number of blocks in ticks is 400. Okay, so this part is a little bit complicated. So there are a few ways that this join can be done. The first type of join that we are going to consider is a nested loop join. Okay? A nested loop join. So in the nested loop join, what is going to happen is that we have to load in so-called rather compare tuple by tuple. So there's no block loop here. So we have to load in tuple by tuple. Okay. So let's see how we come up with the worst case scenario and also the best case scenario. Actually, the best case scenario is easy to think of. In the best case scenario, what is going to happen is that you will just transfer the blocks, excuse me, number of blocks from table S and number of blocks from table R into memory, and then after that you'll do the so-called the comparison tuple by tuple for all the blocks. Okay, so this is this is easy to, not easier, this is the best case scenario, so slightly easier to understand. Okay, the worst case scenario is when this occurs. Okay, the worst case occurs is when only one block for each relation is able to fit into the buffer. Okay? So this is the very worst case scenario. So what will happen is that we have to load each block one by one. Okay. The number of transfers is slightly easier to understand. Okay. And for this one, you have to see how to say, there's a difference in the outer loop and the inner loop. So you notice that number of transfers is going to be the BR, the blocks in the outer loop, which is here. And this one you realize that this is NR, which is the tuples in BR. So for each tuple in BR, I have to load the block. So you can tell this is an expensive operation, right? For each individual tuple in my outer loop, I have to load the block. And so this is a very expensive operation in terms of the number of block transfers that it costs. Okay, so this is how we interpret this part. The seeking is slightly easier to understand. The seeking is the number of tuples in my outer block plus the number of blocks in my outer block. So for each block, I have to do one block seek, and for each tuple in my outer table, I have to do another seek operation. Okay? So this is how we understand and interpret these very complex formulation. Actually, if you understand them, it's slightly easier to appreciate. Yeah, so rather than memorizing them, try to see how we can understand the number of transfers, the number of seeks that or accesses that your loop needs to go through. Okay. Okay. Then I'll go on to the next example. Okay, so this is the nested loop join. So tuple. The next one is the block nested loop join. So this is a improvement. For each block, we do a loop of BR of the outer loop, and then another loop in the inner loop. So there is a block nested loop over here, and then thereafter, then do we do the comparison between the tuples. Okay. The best case scenario is again easier to understand. The best case scenario is that the number of transfers, or rather everything can fit into the memory. So we can just put everything in the memory, and then we just require the block transfers to be number of blocks in each tables add together. And then we have 2 seeks. Okay. Excuse me. So this is the slightly easier one to understand. Okay, let's look at if in the worst case scenario, what happens. Okay. In the worst case scenario, the buffer memory only holds 1 block for each relation. So I can only hold 1 block of BR, and I can only hold 1 block of BS. In this scenario, let's look at the number of block transfers. Okay, we only need to, for the outer loop, we load 1 every single time. So every single time we go through the outer loop, we load it 1 time. So the number of transfer in the outer loop is going to be BR. Okay, this one is slightly easy to understand because outer loop, so every time you load outer loop, load 1 time, so you have only BR for the outer loop. Now let's look at the inner loop. In the inner loop, it loads for every single block of BR. So it means that for every single outer block, I will load 1 time of my inner block. And so in my inner loop, my loading of my block transfer is going to be BR times BS. So this is in my inner loop. You contrast this with my earlier one, which is N. Okay, so in the earlier scenario, every single tuple we need to load my block 1 time. In this scenario, every single block I load my block. Every single block in my outer loop, I load my inner block 1 time. So that's why the cost here is going to be cheaper than that of the tuple nested loop join. And that's how we derive this expression over here. Okay. So here, the fortunate case is that the number of disk accesses is going to be just that 2 times that of the outer loop. So compare with this, in this outer loop access BR times, and every single time the inner loop runs, or rather the outer loop runs, is NR, which is the number of times the outer loop runs. If we compare this with the block nested loop, what happens is that instead of this, we just can replace it with the PR, which is the number of times the outer loop runs, and hence the number of accesses is just 2 times the number of blocks in my outer loop. Okay. 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 Let's go and look at some. If we were to calculate this out, this is the running example. Assuming that student is outer, text is inner. If I have a nested loop join, okay, the best case scenario is easy to see, which is just always 2 and always number of blocks plus. Okay. So the best case scenario is easy to see. So this is again the same thing. Best case scenario. It's the same for both. So it's slightly easy to see. Okay. Let's look at the worst case scenario. In the worst case scenario, for my block nested loop join, my number of disk access is equals to 2 times my number of blocks in my outer loop, which is 100. So that's how I get 200 over here. And the number of transfers is equals to first my outer block plus, or rather the number of my number of blocks in my outer loop excuse me, plus the number of blocks in my outer loop times the number of blocks in my inner loop, which is how I get this number over here. Okay. Okay. Let's compare this with my nested loop join. In my nested loop join, the number of accesses is equals to my n of my outer loop, which is my student, plus my number of blocks of my outer loop, which is 100. And so this is 5,000 plus 100, which gives me 5,100 over here. The number of transfers is equals to the number of blocks of my outer loop first, plus the number of tuples in my outer loop, times the number of blocks in my inner loop. So you can tell this is a very expensive operation. Let's compare with this one. Yeah, so Jia Wei asked me about the number of nested loop join. This okay, can. So the number of disk access for the nested loop join. Okay, so the number of disk access for the nested loop join is you can consider that to be the number of disk access first in my outer loop. So at the very first, every time I do beginning of the loop, I need to do one disk access. Okay. So every time I do this, I need to do one disk access, and so that is number of times is BR, because that is the number of times I'm doing the access. And I'm also doing the number of times I'm doing the next disk access is going to be NR, which is the number of tuples in total in my outer loop. So there's one, there's one instance of a disk access here, another instance of a disk access here. This occurs PR number of times, and this occurs the number of tuples here, which is NR number of times. And so the number of disk access for the nested loop join is going to be equals to NR plus the BR. Why isn't it NR times BR? Let me think. Big question. Why is it NR times BR? Oh no, it is not NR times BR. It is not NR times BR. How can I? No, it's not. So let me see if I'm thinking this correctly or not. No, it's not NR times BR. How do I put this? So it's like, oh, okay. So it's like how like I equals to 1, and for each, right, I equals to I plus 1, right? So after the end of this, right, my I is going to be equals to B, sorry, I will be equals to NR. So this accounts for this one. Because this runs for NR number of times. So if you want to say is a multiply, right, BR times NR, right, it is not this. It should be BR times NR divided by the number of the number of tuples in a block. If you want to like put it in this form that you are saying, right, it should be something like that, which will come back with NR again. I don't know if I can say this properly or not, but what is happening is that this part of the this access, right, it runs for NR number of times. Is that am I making sense? So if okay, so maybe I can explain in this way. If we look at that, right, from a for loop point of view, the number of times this part runs, right, is equals to is equals to is equals to NR. How to put it? Okay, I know already. Okay, I know. Okay, so you see, for each tuple BR in TR in BR, do this. Okay, so by right, this will run. If I do this one time, this will run TR times. Correct. The outer loop run for BR times. Yes. The inner this thing will run for NR times. So this thing will run for BR times. So when we use the NR, right, it is already taking account into what we normally do, the multiplication of the inner and outer loop. It is just that because we know that every tuple, it must load this new block. So that's why we can directly say that this is NR. And also because we know that every time in the outermost block, outermost loop, we know that this would be doing the seek BR number of times. And so the number of these accesses there is going to be BR accesses. So that's why we can we don't need to do that multiplication, and we can immediately say that this is the output. If we do counter a loop, mm, okay, let me think. Maybe I shouldn't have used that loop kind of analogy. What maybe okay, let's say I equals to 0 for something I plus plus for something, then I don't need to do anything here. So what is happening is that then I will be equals to n. So maybe what I mean to say is that so this is how to say for each tuple in VR. So let's say I plus plus. So so it is here. So by right, and how to put it, and this will run for each block as well. So you see, let's say in each block there is 10 tuples. So I will be equals to 10. But if let's say there are 5 blocks in BR, this will run for BR times, and so this will be 50. And so this will be the number of tuples in BR, which is NR. Is this clearer? Wait, is this clearer? Okay, okay. I do one more time, then we take a break, and then we will revisit this again. Sorry, this one like take a lot of time. Okay, but it's good. It's a good question to clarify. Okay, let's say this table R has 50 tuples. Okay, and let's say 10 tuples in one block, and so R has 5 blocks. Okay, S actually we don't need to care because S is not in the picture at all. Okay, so what is happening is that I have for each tuple in BR. Okay, but then after that, then let's say I have I equals to 0 here, I plus plus. Okay, so 4. But this one I don't need to care. Okay, then I want to find what is my value of I. For each tuple of BR, by right, this will run 10 times. Correct? Because each block has 10 tuples. Okay, this outer loop, actually this one will run for 10 times because each block has 10 tuples. Okay. But we also have to remember that this will run for the number of blocks as well, because we need to iterate through all the blocks. So we will then iterate through all the blocks, which is 5 blocks. And so for each block, the number of disk access here is equals to 10. But because there are 5 blocks in my R, and so I need to multiply by 5. And so this turns out with 50, which is the number of disk access, which is the number of tuples in my R. Because essentially what is happening is that for every tuple we need to do one disk access. So yeah, so of my inner block. So that is it lah. Is that clearer? Or is it still as confusing? Okay, okay, never mind. It's normal. Yeah. So yeah, that's why I say actually this part is a little bit confusing. Little bit confusing. Maybe if there is a little note here to say that this runs for all blocks, maybe it'll be easier to understand. Yeah. So yeah. But okay. But it's a good question to clarify. So I think what? Let's take a quick break. So thank you so much for your questions before the break. So as I said, this part can get a little bit heavy. Sometimes like why like that, why like that. So maybe take some time to digest through. Okay, let's look at the next example, which is the nested. Okay, so just now we talked about the nested loop join. So why do I have 2 nested loop join here? It's like, like, is it strange? So why I have 2 is that this is the student outer takes inner join. This is in my takes outer student inner join. Okay, so I in this one I actually switch the loop yeah thing. What's the word? What's the word? The loop. Yeah. So anyway, I switched the loop. Yeah. So here, the best case is still the same. And then now let's look at the worst case. The worst case is that okay, let's look at the transfer, because transfer is slightly easier to see. The transfer is going to be the number of blocks of my outer loop. So which is 400. So now this is my outer loop, plus the number of records in my outer loop. So this is 10,000. And I need to multiply it by the number of blocks of my inner loop. Okay, because this is a nested loop join. So I need to take the number of blocks of my outer loop plus the number of records multiplied by the number of blocks of my inner loop. So this is what I get. This is in the transfer. In the seek or the access, I will need first the number of blocks in my outer loop, which is 400, plus the number of disk accesses in my outer loop, which is 10,000, which is the number of tuples in my outer loop. And so this is the number of disk accesses we need. Okay. Okay. So this is still fine. The next one is where it gets a little bit confusing again. So now we have the indexed nested loop join. Yeah, this this is quite confusing. Yeah. Okay. So this is confusing in the sense of by now, actually I have an index that occurs. And okay, let's look at the, okay, there's no worst case scenario, there's no best case scenario. Let's look at the worst case scenario. The worst case scenario is that the buffer only holds one block of each of my table. Okay. So if we okay, to look at this example like this, right, it's very hard to see, especially when we look at this C, right? This C is actually the cost of a single selection. So actually look at that, right? It's very hard to understand. Okay. The easy way to understand is that we remember what we did the last time, which is something like this. So there's two costs that's being involved. The cost in the height and the cost over here, okay, in the leaf. Okay, so if we look at it from this perspective, it's slightly easier to understand. So recall that there's a cost that is being incurred as you traverse down the tree. And typically, last few lectures at least, we didn't go into detail of this, but this we need to calculate based on the height of the tree. To understand this formula, this easier to go through an example, which is this example. Okay, let's look at this indexed nested loop join example, where my student is in the outer loop and my ticks is in the inner loop, and the index is on the ticks. Index is on the ticks on the attribute ID. Okay. 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 So this is the nothing else has changed. Nothing else has changed. The only thing that has changed is that right now my ticks has an index on ID. Okay. Other than that, nothing else has changed. Okay. It also says that on average, I have 20 entries in each index node. And so it says that on average, I have 20, 20, 20, or rather like that, 20 here, on average. So what this means is that I can calculate the height of my B plus tree. Okay. So my height of my B plus tree is going to be equals to my number of records here, because it's ticks, log of 20, log base 20, which is equals to the number 4. Okay. So this is equals to 4. H is equals to 4. Over here, this is equals to 4. Okay. Okay. What? So now we have the number of this access to be, or rather the number of level to be equals to 4. Let's look at the number of seeks and the number of transfers. Okay, let's go back to this which one should we use? Let's see, which one should I use? I think we use this one. Okay, if we go and understand what this is doing, I have my outer block multiplied by the time taken for my seek and my transfer. Over here, I have my outer block, which is equals to my student. So my student is equals to 100 blocks. And wait, this is 5,000 records. This is equals to my number of tuples. Hold on. Why is it like that? So I have wait, let me check this. I went through this just now only. C is the cost of selection down. Okay. Sorry. C is the cost of selection down. C is the cost of selection down. So C is equals to this number, which is 4 plus 1 multiplied by my this number, 4 plus 4 multiplied by this number. Let me think through. Okay, I'll tell you what. Let me defer this again. I will think through how I got these numbers again, and I will get back to you very soon. I thought I went through this just now. Sorry, I thought I got the numbers correct just now. Sorry. Yeah. Let's go through this one first. Actually, for this is very similar to what we do for the merge sorts. So what we are doing is that in this merge sort example, we have two buffers, and what we do is that we just read all the records in one table and that in another table as possible, and then we put the first pointer at the start. As and when we can, we will read the so-called the smaller one, and then we put it into the buffer, and then we will increment the buffer along the way. So A comes, and then after that A, and then after that B and B and C and D. So actually this is just just a simple sort merge operation, very similar to what we had in the merge sort algorithm. So I don't go into detail in this. Okay, in the sort merge join cost analysis, what we do is that the block transfers, each tuple is only read one time, and so the block transfers for each block is going to be both for the block number of blocks in my tables, and same thing for the number of disk access is also going to be the number of blocks in each of my table. Okay. So this is going to be, let's say if I have R, if I have S, the number of blocks here, I will need to read each only once. I need to do a disk access for each block only once. And so the cost of this will be equals to BR times BS, number of transfers, as well as the number of disk accesses. Okay. Okay, I hope this is slightly clearer. Okay, let's look at this is what we call the complex join. Okay, so in the complex join, let's say if we join with a conjunctive condition, which is a lot of n conditions over here, what we can do is we compute the intermediate results and we return the intermediate results that satisfy the remaining condition. So what it means is that if let's say they are how to say, if let's say there are 5 conditions, and then if after I do this join, I end up with 3 tuples. So let's say these 3 tuples are run with 2 conditions already. So there are 3 additional conditions. So when I return, I can then, in a way, return only the tuples of these 3 that satisfy the remaining conditions. Okay, so this is what this portion actually means. Okay, and the join with a disjunctive condition actually merely means that I will do, or rather one possible way to do it is that rather than doing OR for every single condition, which may be an expensive operation, what will be done is we will do a join and then followed by a union between all the operators. To be frank, both of these are pretty expensive. Yeah, so both the join and both of these, either you do it at the theta condition or at the joint conditions, both of these are actually pretty expensive operations. Okay, let's look at the next example. So again, this is a duplicate, very similar to that of your typical merge join, which is just that if they have if they have duplicates over here. So let's say duplicates sorry, not yet. So this is just the runs. So this is the divide stage, and this is the conquer. So this is division into the runs. So right now we divide, and then the duplicates are actually not removed yet. They are removed only in the conquer stage, and even the conquer stage, you can see when they are removed. So they are removed when it comes from the same run. Okay, so when it comes from different runs, it is not removed yet. So only when it comes from the same run, there would the duplicated so-called entries will then be moved. Okay, this should be clear. So we have set operations. So we have union, intersection, and the set difference. So how this can be done is we would sort the relations, and then we would scan through each to produce the result. So for these operations, typically sorting it first somehow seems to be the better option. Of course, this will be expensive operation. So we do the after we do the sort, we will scan through each of the sorted relations to produce either the union or the intersection or the subtraction. Okay, so these three are actually just to explain the operations. So only when they're in both files, or rather, they will be they'll be placed in if they appear in either of the files. Intersection only in both. We retain those that absent in S for R minus to S. Okay, for this one, we don't look into the merge sort cost. We just look at the block transfers, and this is quite clear because we have the number of blocks in BS, the number of blocks in BR, and so this is typically just the number of blocks and in both of the tables add together. Okay. Okay, let's look at the next slide. So there are three ways whereby expressions can be evaluated. The first is called materialized. Materialized means that we actually keep it in a temporary relation. Yeah, so we store it somewhere. We store it somewhere. So that's why we call it materialized. So of course, the disadvantage is that there's data cost that's being that be involved. But advantage is that you can always use it. So no matter what is the situation, this materialization can always be used. Okay. Then of course we have pipeline, which means that the result of one is directly passed to the result of another. Yeah, so there's no need to store temporary relation. So this is the pipeline, and the last is double buffering, which use the two output buffers for each operation. Yeah, so we will not be focused too much on these techniques, but I think this is just to let you understand that these are some of the ways that we are able to carry out to evaluate the operations. So in terms of materialization, so what happens is that, for example, in the drawing conditions, or rather in the drawing conditions, what is possible is that we will be able to write it back to disk, and it doesn't matter if this drawing is very big or what, it will always be able to work in materialized settings. Pipeline usually does is that you do it in the project operator. So let's say, or even in the Sigma operator. So this is a materialized drawing, and this can be a pipeline. So when the drawing operator generates a result, you can pass it directly to the project operator to come up with the final result. Yeah, so typically for pipeline, you use it for selections, you use it for projections. For materialization, maybe you want to be a bit safer and use it for joins. Yeah, so if you use pipeline for joins, of course, the danger is that your memory may not be able to fit everything. So that will be so that will be the issue. Okay, so pipeline just means that you pass it on to the next operator for processing. So there are two types of pipelines. One is the demand-driven pipeline. The other one is the producer-driven pipeline. Yeah. So in the demand-driven pipeline, the system will make repeated requests for the tuples at the top of the pipeline. Okay, so what happens is that you will request for the join to give you the data. So there is the demand driven. So let's say if there's a projection here, so this will demand the join to start to give them the data, whereas the producer one will be the join producing the data and eagerly passing it on to the projection operator. Okay. The next part is another big topic. It is on query optimization. So what happens is that in query optimization, it is the process of selecting the best query to evaluate. So this we see here is a relational algebraic expression. There are many ways to execute a relational algebraic expression. And it depends, depending on the way you write the algebraic expression, the cost that it will incur is going to be different. So we will, in this example, what we have is that we have a projection first of the course with a join to the teachers and a join to the instructor, a selection based on music with a projection of the name and the title. Okay, so if we were to draw out the tree, this will be what it will look like. So this is what this initial one looks like. So I have the projection, I have the selection, I have the join of the instructor with this condition, and I have another join with teachers with this, and the projection on the course. So this is my initial expression tree. Okay, so what we tend to see is that this is an expensive operation, or rather the initial expression tree may be an expensive operation, meaning that this is not optimized yet. There's ways that we can optimize this initial tree. And some of the ways that we can optimize this tree is that, for instance, there is this selection operator. If you are able to push the selection operator before the join condition, then it will make the query cheaper to execute. So in this scenario, what is happening is using one of the relational algebraic rules to push my sigma operator down to my instructor, and so it ends up with this as my my sigma being pushed into my instructor. And so if I were to draw my algebraic expression tree, I will end up with sigma. Maybe I look at this one first. Projection of name and title with a sigma here, with a join here, and a sigma based on instructor with a join of teachers, and again projection of course ID title with a course. Okay. 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 So we may want to go one extra step to say that, okay, so from here we can send this as a pipeline. This one maybe is a materialized join. This is we can send this to be like a pipeline. This can be another materialized join, another pipeline. So if we want to so-called put down even the so-called how it is being executed, we are able to do it. But typically for this module, I'm happy if we can stop here. I think this is okay. We don't need to go up to this level to show the pipelines or the materialization. Okay, so this level I think is good enough. Okay, let's look at the steps. So we have the initial expression, and we generate using equivalence rules, and we estimate the cost of each so-called plan, and then we find the query plan with the lowest cost. Okay, so typically that's how we try to generate the lowest cost for a plan. So this is actually a form of heuristic. So of course we can enumerate all the possible plans out, and even with the usage of dynamic programming, it's going to be extremely expensive. Actually, if we use they call it a left deep tree, and we use it to generate out the best plan, it's still going to be big O of n to the power n. If it's a bushy tree, it's going to be 3 to the power n. So this is a very expensive operation, even with the usage of dynamic programming. Yeah. So what we are showing in this module actually is more like a heuristic, how we can easily estimate the costs of different plans. So we went through this earlier, which is the cost analysis of merge sort. Okay, so on this, we will go through this in more examples in the next lecture. Okay, so let's look at this example first. Rather, this is the cost analysis for that of a merge sort. We have two examples to go through. Let's look at the first example first. So suppose you need a sort relation of 40 gig, a block size of 4K, memory size of 40 M. Suppose the disk transfer rate is 40 per second. How many, so the first question is how many merge passes are required? Okay, so you want to try this for a while first? To find out the number of merge passes, you want to find out the number of blocks in memory. So the hint is that my relation is 40 gig. my block size is 4K. I want to find out how many blocks are there in my relation. And I also want to find out how many blocks can fit into memory. I don't know. I didn't upload, is it? I will upload later. If I forgot, I will upload later. Okay. So yeah, I think maybe I forgot. I'll upload later. Thank you. I can't upload now. Maybe you take about 1-2 minutes to solve this while I upload the slides. Okay, the slides are there already. I just uploaded them. Yeah, so if you need any formulas, they are there. Okay, okay, let's go through this one first. Let's go through this one first. Okay, okay, let's go. Okay, let's go through this one first. Okay, let's do it. So first I want to find the number of blocks in the relation. So number of blocks in relation will be 40 gig, which is times 10 to the power of 9 divided by 4. Let's do the easy one. So this is 10 to the power 7. Okay. So number of blocks in memory, which will be equals to, the memory size is 40 million. So 40 times 10 to the power 6 divided by 4 times 10 to the power 3. Which is so this is 10 times 10 to the power 3. Yeah, also this 10 to the power 4. Okay. So the number of passes equals to what is the formula? Log m log 10 to the power 4 minus 1 and number of blocks in the relation divided by number of blocks that can be held in memory. So this is 4. So this will be equals to, not wrong, this is equals to 1. Okay. So this is how we solve this 1A. Okay. 1B, I leave you all to solve it first. But before that, I realized that okay, give me a chance to redeem myself with this question, because I realized, because I went through this question, maybe I confused myself. I think I confused myself in this question. Okay, so let me give me a chance to redeem myself. Okay, so firstly, I have this is the index nested loop join. Okay, now I kind of remember what went through my mind already. Index nested loop join. Let's look at first the transfer. Transfer is that for every, my outer loop is my outer loop is where? Outer loop is my student. Inner loop is my text. So I will need to loop through every single time my outer loop, correct? I think so. Yes, I remember I was going through this afternoon only. So every single block of my outer loop, I need to do a transfer. Okay. In the inner loop, because it's an index join, so every single so-called tuple in my outer loop, I also have to check. And so because I have a single outer loop, I need to check. So that's why I have this 5,000 in my outer loop, right? Because I have 5,000. What is the cost of my access to my inner loop? My cost of my access is going to be just 5 because of my index. Okay, so that's how I come up with this number for my transfer. So for my transfer, what is happening is that for every outer iteration, there's 100 blocks of my outer iteration. For every single tuple of my outer block, which is 5,000 tuples, what's happening is that I need to do a search of my index. And my search of my index will require log 10,000 base 20, which is 4 plus 1, which is 5. Okay, so that is the amount of transfers that is required in my index nested loop for my nested loop join. Okay, in the same way, the number of disk accesses that is required is going to be the same as the number of these transfers, which is why we see that these two numbers are the same. And in this particular scenario, it will always be the same, because the number of times that you will do my disk transfer is going to be similar to what we analyzed in the past, in the last 1 or 2 forms of joins. So you always need the disk access before the before the outermost loop, and then for every single tuple, you will need to do a disk access at every single level again. Okay, so every single level again, we need to do another disk access. Okay, so yeah, so that was what I I remember that was how I solved this thing. Okay, I forgot how, or maybe I didn't went to correlate it back to these two slides. I will think how to correlate it back, or rather I will try to figure out how to correlate it back to these two slides in the next lecture. But hopefully this clarifies the doubt. Sorry that I don't know why just now I was confused or don't know what. Suddenly I like forget what I was going to say. But this is how we explain this slide. Okay, now my time is it? Yeah, my time is just right. Thank you so much for your time this evening, and I wish you a pleasant pleasant night. I will see you on Thursday. Have a good evening. Bye bye. Thank you. I will stop recording.